Now in this lecture we'll answer two questions. In the first question we find out the area of rectangle ABCD that blocks this circle, and in the second question we find out the area of this trapezoid ABCD. So we start with the first question. In the domain we have rectangle ABCD, and this circle is inscribed by rectangle ABCD, or rectangle ABCD blocks this circle. In addition, we know that this is called EF, that is equals to 12 units in its length. This is line segment FG, that is equals to 10 units. Again, our mission is to find out the area of this rectangle ABCD. Okay, so first of all, we know that all the angles inside any rectangle are right angles. So all those four angles are right angles. So this is a right angle. We know that the area of any rectangle equals to the length of the rectangle times the width. So we define the width of this rectangle ABCD as dA. And we will define the length of this rectangle ABCD as AB. We define the radius of this circle as R. Point O is the center of the circle. Point N is the point of tendency of tangent AB in this circle. So point N is a point on the circle itself. Therefore, ON is the radius of this circle. That is equals to R according to our definition. The radius ON is equals to R. The radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we will join points O and M together by a straight line. OM is of course the radius of this circle is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Point E is the point of tendency of tangent DA with this circle. So we join points O and E together by a straight line. OE is of course the radius of this circle, that is equals to R. Again, the radius OE is drawn to point E, that is the point of tendency of tangent AD with this circle. And whenever your radius is drawn to the point of tendency, then tangent AD will be perpendicular to the radius EO. If AD is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule 1. So actually, by doing this construction, you gather there the small quadrilateral DMOE. Inside the small quadrilateral DMOE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, in total it must be equal to 360 degrees, according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this 4th pieces angle must be equal to 90 degrees in its size. In the next step, we focus on the lower quadrilateral EO and A. Inside this lower quadrilateral EO and A, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees, according to the same rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in its size. So actually the big angle MON is equal to 90 degrees plus 90 degrees, that is 180 degrees. So if you know, the big angle MON is equal to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. So MON, or line segment MON, is a straight line. If MON is a straight line, then MN is also a straight line. So MN is a straight line that touches the circle at 2 points, point M and point N, and therefore MN is a chord. MN is a chord. It is a chord that passes through point O, that is the center of the circle, and you know that any chord that passes through the center of the circle must be the diameter of the circle. So it is known, MN is a chord that passes through the center of the circle, that is to say point O, and therefore MN is the diameter of the circle. So we should find out that MN is the diameter of the circle. So it is known, MN is the diameter of the circle. In the next step, we will extend the radius EO that is equals to R by a straight line until it touches the circle. and we will define the touching point of the extended radius EO with this circle. This point is point L. So we extended the radius EO, that is a straight line by straight line, and the result is EL. When you extend the straight line by straight line, the result must be also a straight line. So EL must be a straight line. EL is a straight line that touches the circle at 2 points E and L, and therefore EL is a chord that passes through point O, that is the center of the circle. Therefore EL is the diameter of the circle. So can I tell that EL is the diameter of the circle. So we know that the width of a rectangle ABCD is equal to DA. So let it known. The width of a rectangle ABCD is equal to DA, and MN is the diameter of the circle, which is absolutely a straight line. So this shape DMNA has in total 4 sides: 1, 2, 3, 4. Therefore it is a quadrilateral. And in quadrilateral DMNA we have 4 angles. So write it down. In quadrilateral DMNA we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must meet this rectangle if not a square. So we will let to quadrilateral DMNA as a rectangle because it has 4 right angles. So the big quadrilateral DMNA is a rectangle according to rule 5. But we also know that so I write it down, the big quadrilateral DMNA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. MN equals to the opposite side DA. So can I tell that DA equals to MN? And we already found out that MN is the diameter of the circle. So write it down, MN is the diameter of the circle. But we also found out that EL is also the diameter of the circle. So can I tell that EL is the diameter of the circle also? And from this long equation, the width equals to DA, and DA equals to MN, and MN equals to the diameter, and EL is also equal to the diameter. We will derive that the width of rectangle ABCD is equal to EL. Okay, the width of rectangle ABCD is equal to EL, or EL is the width of rectangle ABCD. Yeah, EL equals to the width of rectangle ABCD. In the next step, we will join points L and F together by a straight line. By joining points N and F, we create the peripheral angle LFE. This is peripheral angle LFE that subtends on EL, that is the diameter of the circle, and we know that according to Rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So I repeat quickly on Rule 7. According to Rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing here a circle, AB is the diameter of this circle. This is peripheral angle ACB that subtends on AB, that is the diameter of the circle, and therefore according to this Rule 7, the size of peripheral angle ACB is 90 degrees. So any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size according to this Rule 7. So can we implement Rule 7 in our drawing? Why? Because in our drawing we have peripheral angle LFE that subtends on EL, that is the diameter of this circle, and therefore according to Rule 7, the size of peripheral angle LFE is 90 degrees. In the next step, we define this angle LEF as alpha. So in the right angle LEF, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in a triangle. So in the next step, we will extend the diameter EL by straight line until it touches side CB of rectangle ABCD. And we define the touching point of the extended diameter EL with side CB of rectangle ABCD. This point is point C. By doing this construction, we created here the big quadrilateral ETBA. So in the big quadrilateral ETBA, we have 1, 2, 3 angles. The sum of 3 angles is 230 degrees, so 230 degrees plus the size of this 4 pieces again, in total they must be equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces again must be equal to 90 degrees in its size. So inside the big quadrilateral ETBA we have 4 angles. And according to Rule 5, any quadrilateral that has 4 angles must be this rectangle if not a square. So related to the big quadrilateral ETBA is rectangle because it has 4 angles. So I write it down. The big quadrilateral ETAB is a rectangle according to Rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side BA. So let me know. In rectangle ETBA, side ET must be equal to the opposite side AB. ET equals to AB. But AB, according to our definition, AB is the length of rectangle ABCD. So it's imagine that AB is the length. And for this expression, ET equals to AB equals to the length, we derive that ET is also the length of rectangle ABCD. Or the length of rectangle ABCD is equal to ET. So if we found out that the width of rectangle ABCD is equals to EL and the length is ET. The next step we will focus on the big right triangle ETG. In this big right triangle ETG, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in a triangle. It is very easy to see that the big right triangle ETG is similar to the small right triangle ELF according to angle similarity rule. That is to say, this is angle E, that is also defined as angle alpha. It is a common angle that belongs to both angles. Angle E belongs to the big right triangle ETG, and angle E of course belongs to the small right triangle ELF. So we can find out that angle E equals to itself is a common angle that belongs to both angles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the angles of the big right triangle ETG are correspondingly equal to all the angles of this small right triangle ELF, and therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. If you found out that the big right triangle ETG is similar, this is sort of similar to the small right triangle ELF, according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. So repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side, so we leave it as it is. Over EF. EF equals to 12 units in its length according to what is given as the question. And it is equal to EG. EG in total equals to 12 plus 10, that is 22. Over EL. EL is the missing side, so leave it as it is. So in total, if we found out that ET over 12 equals to 22 over EL. Here we'll first multiply this equation and we get that ET times EL is equal to 22 times 12. Again, ET times EL equals to 22 times 12. So ET times EL is equal to 22 times 12. 22 times 12 is 264. So in total, if you found out that ET times EL is equal to 264. But we already found out that ET is the length of rectangle ABCD and EL is the width. So we substitute ET by the length and we substitute EL by the width. So the length times the width of rectangle ABCD is equal to 264. The length times the width is the area of rectangle ABCD. So if we found out that the area of rectangle ABCD is equal to 264 square units. And that is the answer to the first question. I'll repeat again. We actually found out that the area of this rectangle ABCD, that is the area that we are looking for in this question, is equal to 264 square units. So we finish with the first question. In the next step, I'll present to you the second question and we'll solve the second question of this lecture. In the second question, our task is to find out the area of this trapezoid ABCD. It is given us the question that side AB equals to line segment AP. Likewise, side PD equals to line segment PD equals to side DC. We also know that this is angle PQC, that is a right angle. Those two angles are also right angles. Line segment BQ equals to 4 units in its length. Line segment QC equals to 9 units in its length. Again, our mission is to find out the area of this trapezoid ABCD. So we know that AB equals to AP. So if we define the length of side AB as A, then the length of side AP must be also equal to A because they are equal to each other according to what is given as the question. Likewise, if we define the length of line segment PD as B, then the length of line segment DC must be also equal to B because they are equal to each other according to what is given as the question. In the next step, we join points B and P together by straight line. And we join points P and C together by straight line. By joining points B and P, we created the right triangle APB. This is a right triangle that is also an isosceles triangle. Why? Because side AB equals to side AP. So we know that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other because they are located in front of those two equal sides. So if we define the size of this angle is alpha, then the side of this angle must be also equal to alpha because they are equal to each other, according to the rules that I mentioned. We know that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in this triangle, triangle APB. So each angle we have in the small triangle, triangle ABP, in the small right triangle APB, we have this angle that is a right angle plus those two angles. Each of them is equal to alpha, so it is 90 degrees plus 2 alpha. In total, it must be equal to 180 degrees according to the rule that said that the sum of the angles in a triangle is equal to 180 degrees. So here we subtract 90 degrees from this equation, and finally get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we divide this equation by 2, and finally get that alpha equals to 100 degrees over 2 is 45 degrees. So if you found out that this is angle alpha that is equals to 45 degrees in size, and this is also angle alpha that is equals to 45 degrees in its size. Therefore, we can conclude from what we did until now that any right triangle that is at the same time an associated triangle, you have always the same angles. One of them is 90 degrees, and the two other is 45 degrees. So therefore, in this right triangle PDC, that is also an associated triangle, because PD equals to DC, therefore it is also an associated triangle. Those two angles must be equal to 45 degrees intersected each of them. It is so in any right triangle that is also an associated triangle. So those two angles must be equal to 45 degrees in their sizes. We know that AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the right side of the straight line AD at point B, here the sum of the angles must be equal to 180 degrees according to rule 3 that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD at point B? We have this angle that is 45 degrees plus this angle that is also 45 degrees. So 45 degrees plus 45 degrees is 90 degrees. So 90 degrees plus the size of this first missing angle, in total it must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. Why? Because 90 degrees plus 45 degrees plus 45 degrees is equal to 180 degrees. That is the sum of the angles on the right side of the straight line AD at point B according to rule 3. So therefore this missing angle must be equal to 90 degrees in its size. Actually, the missing angle, the missing angle is angle PBC. So this is the missing angle BPC, that is the right angle according to rule 3. So in the next step, we define angle BPQ. This angle is alpha. So what is the size of this angle? Angle CPQ. Angle CPQ must be equal to the big angle that is the right angle minus this angle that is alpha. So in total, angle QPC must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is the size of the big angle BPC. Angle BPC is right angle. So this missing angle must be equal to 90 degrees minus alpha. So in the right big triangle QPC, this angle equals to 90 degrees, this angle equals to 90 degrees minus alpha, therefore this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle, actually, this angle is a right angle. Why? Because you know that BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the left side of the straight line BC at point Q here, the sum of the angles must be equal to 180 degrees according to rule 3. So 90 degrees plus the size of this missing angle, in total they must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size, according to rule 3 of course. So in the small right green triangle BQP, this angle equals to 90 degrees, this angle equals to alpha, therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. So this missing angle must be equal to 90 degrees minus alpha. It is very easy to see that the green small triangle PBQ is similar to the big right triangle PQC according to angle similarity rule. That is to say, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, and therefore they are equal to each other. So if you prove that all the figures of the big right triangle PQC are correspondingly equal to all the figures of this right small green triangle PBQ. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. So if you follow the big right triangle PQC, is similar, this is the sign of similar to the small green right triangle PBQ according to angle similarity rule. And for the fact that the green right triangle is similar to the big triangle PQC, we derive that the following relationship exists between their sides. We will derive, but before that, PQ is a common side that belongs to both triangles. PQ belongs to the small green triangle PBQ, and PQ also belongs to the big right triangle PQC. So PQ is a common side that belongs to both triangles. So from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. So I mentioned 1 minute ago, PQ is the common side that belongs to both triangles. So, repeat again. From the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. The side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PBQ. So PQ is the missing side, so we leave it as it is. Over BQ. BQ equals to 4 units in itself, according to what is given us the question. And it is equal to QC. QC equals to 9, also according to what is given us the question. Over PQ. PQ is the missing side, so we leave it as it is. In the next step, we cross multiply this equation, and we get that PQ times PQ is PQ squared. And it is equal to 9 times 4, that is 36. So in total, we actually found out that PQ equals to 36. Here, we take a root out of this equation, and finally we get that PQ equals to the square root of 36, that is 6. So the missing side PQ is equal to 6 units in its length. This is the missing side PQ, that is equal to 6 units in its length. In the next step, we'll implement the Pythagoras theorem of the big right triangle BPC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the provision for Pythagoras theorem. So according to the Pythagoras theorem, in this big right triangle PBC, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. BC is the hypotenuse, so the square of the hypotenuse is BC square. And it must be equal to BP square plus PC square. So in total, according to the Pythagoras theorem, in the right triangle PBC, the right big triangle PBC, BC square equals to BP square plus PC square. BC in total equals to 4 plus 9, that is 13, therefore BC square is 13 squared, that is 169. And it is equal to BP square. What is the value of BP square? We focus on the small right triangle ABP. According to the Pythagoras theorem, on the small right triangle ABP, A square plus A square equals to PB square. A square plus A square is 2A square. So PB square is 2A square plus PC square. What is the value of PC square? PC is the hypotenuse of the right triangle PDC. Therefore, according to the Pythagoras theorem, B square plus B square equals to PC square. B square plus B square is 2B square, so PC square equals to 2B square. So in total, we found out that 169 equals to 2A square plus 2B square. So 169 is equal to, we take out 2 as a common factor from those two expressions, so inside the brackets we have A square plus B square. So in total, we found out that 169 equals to 2 times A square plus B square. Here we divide this equation by 2 and finally get that A square plus B square equals to 169 over 2. Put together, we actually found out that a square plus b square equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. The area of trapezoid ABCD must be equal to the sum of the areas of the three components the trapezoid ABCD consists of. The first component is the right small triangle ABP. The second component is the big right triangle BPC, and finally the third component is the right triangle PDC. So the sum of the areas of those three components must be equal to the area of trapezoid ABCD. So write it down. We actually found out that the area of trapezoid ABCD is equal to the area of the first component that it consists of, that is to say, it is the area of the small right triangle ABP, plus the area of the second component the trapezoid ABCD consists of. The second component is the right triangle PQC, so it is plus the area of the big right triangle PQC, plus the area of the first component that trapezoid ABCD consists of. The first component is the right triangle PDC, so it is plus the area of the right triangle PDC. So in total, we have found out that the area of trapezoid ABCD is equal to the sum of the areas of the three components that it consists of. That is to say, is the area of the first component, that is the area of the small right triangle ABP, plus the area of the second component, that is actually the area of the big right triangle PQC, plus the area of the first component, that is actually the area of the right triangle PDC. So we have to find out the area of each component. We'll add the areas together, and the sum of the three areas will be equal to the area of the big trapezoid ABCD. That is the area that we are looking for in this question. So first of all, we find out the area of the first component. That is actually the area of the small right triangle ABP. This is the small right triangle ABP. We know that the area of any triangle equals to the base of the triangle times the height over 2. We take the base of this right small triangle ABP, SAB, times the height, that is AP over 2. So it is A times A over 2, that is A squared over 2. So the area of the first component, that is the area of the small triangle ABP, is A squared over 2. Plus the area of the second component, that is the area of the big right triangle PBC. Plus the area of the big right triangle PBC. So what is the area of the big right triangle PBC? It is equal to the base, that is BC, times the height, that is QP over 2. So it is BC times QP over 2. Plus the area of the third component that trapezoid ABCD consists of. The third component is the right triangle PDC. And the area of the right triangle PDC is equals to the base, that is DC, times the height, that is DP over 2. DC is B, DP is also B, so it is B times B over 2, that is B squared over 2. So in total, we found out that the area of trapezoid ABCD is equal to A squared over 2 plus BC times QP over 2 plus B squared over 2. A squared over 2 plus B squared over 2 is A squared plus B squared over 2. And we have also the area of the big right triangle PBC. There the big rectangle PBC it is equals to the base that is BC, and BC is 4 plus 9, that is 13, times QP. QP is 6 divided by 2. So in total, if we found out that the area of trapezoid ABCD is equals to A square plus B square over 2 plus 13 times 6 over 2. So it is A square plus B square over 2, and here we have 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. So here we found out that the area of trapezoid ABCD is equal to A square plus B square over 2 plus 39. But we already found out that A square plus B square is 169 over 2. So we substitute A square plus B square here, this expression by 169 over 2. So it is 169 over 2 divided by 2 plus 39. So there trapezoid ABCD is equals to 169 over 2 times 2, that is 4, plus 39. So here we multiply 59 by 4, and then we divide it by 4 in order to have a common factor with this number, and we get that in total the numerator we have 169 plus 39 times 4 is 156 divided by 4, and 169 plus 156 is 325 divided by 4, and 325 over 4 is 81.25 square meters. So if we found out that the area of this trapezoid ABCD is equal to either 325 over 4 square meters, so in terms of numbers, the area of this trapezoid ABCD is equal to either 325 over 4 square meters, so in terms of numbers, it is equal to 81.25 square meters. Okay, so I'll finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our mission is to find out the area of this rectangle ABCD. So in the drawing we have rectangle ABCD, and the rectangle ABCD blocks this circle, or this circle is described by rectangle ABCD. In addition, we know that this is called EF, that is equals to 12 units in its length. This is line 7 PG, that is equals to 10 units in its length. And got our mission to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside the rectangle are right angles. So this angle is a right angle, and this was the missing angle, that is a right angle. Okay, and we know that the area of a rectangle equals to the length of the rectangle times the width. We define the length of this rectangle ABCD is AD, and the width, again, we define the width of this rectangle ABCD as DA, and the length is AB. In the next step, we join points O and N together by straight line. ON is the radius of this circle, that is equals to R, and because of the fact that the radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to all one. Likewise, we join points O and M together by straight line. OM is the radius of this circle, that is equal to R. The radius of OM is drawn to point M, that is the point of tendency of tangent DC with this circle. Whenever a radius is drawn to the point of tendency, then this circle will be equal to 90 degrees, and this circle also equal to 90 degrees according to rule 1. Likewise, we join points O and E together by straight line. OE is the radius of the circle, and because of the fact that the radius OE is drawn to point 8, that is the point of tendency of tangent DE with this circle, whenever your radius is drawn to the point of tendency, then tangent DA will be perpendicular to the radius DO. If DA is perpendicular to DO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to the rule 1, of course. So, in the small quadrangle DMOE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, in total must be equal to 360 degrees, according to the rule that said that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, these 4 pieces again must be equal to 90 degrees in size. Likewise, in the lower quadrangle EONA, we have in total 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, in total it must be equal to 360 degrees according to the same rule that I mentioned. Therefore, this 4 pieces again must be equal to 90 degrees in size. So the big angle MON is equal to 180 degrees. The big angle MON is equal to 180 degrees in its size. And you know that any angle that is equal to 180 degrees in size, it is defined as a straight line. So MON is a straight line. If MON is a straight line, then MN is also must be a straight line. But MN is a straight line that touches the circle 2 points M and N, and therefore MN is a chord. MN is a chord that passes from point O, that is the center of the circle, and you know that any chord that passes from the center of the circle must be defined as the diameter of the circle. Therefore, MN is the diameter of the circle. Again, if you found out that MN is the diameter of the circle. So, MN is the diameter is a straight line. Therefore, in shape DMNA consists of 4 sides, 1, 2, 3, 4, and therefore shape DMNA is a quadrangle. It is a quadrangle that has 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be a rectangle if not a square. So we relate to the big quadrangle DMNA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. Okay, in rectangle DMNA, side MN equals to the opposite side DA. But DA is the width according to our definition. So we can write that DA is the width, and we have already found out that MN is the diameter of the circle. So we can write here that MN is the diameter of the circle. In the next step, we extended the radius EO by straight line until it touches the circle at this point, point L. So EO is a radius which is absolutely straight line, so, and when we extend the straight line by straight line, the result EL must be also a straight line. So EL is a straight line, EL is a straight line that touches the circle at 2 points, E and L. Therefore, EL is a chord that passes from point O, that is the center of the circle, and you know that any chord that passes from the center of the circle must be the diameter of the circle. Therefore, EL is the diameter of the circle. So we can write here that EL is the diameter of the circle. And from this long equation, the width equals to dA equals to mn equals to the diameter equals to EL. We will have that the width of a rectangle ABCD is equal to EL. The width of a rectangle ABCD is equal to EL. So, in quadrangle DMNA, we have 4 rectangles, and therefore quadrangle DMNA is a rectangle, and we know that the opposite sides of rectangle are equal to each other, so dA equals to mn, so we have already done it, dA equals to mn. So in the next step, we added points L and F together by straight line. Finding points L and F, we can derive peripheral angle EFL. Peripheral angle EFL subtend on EL, that is the diameter of the circle, and we know that any peripheral angle that subtend on the diameter of the circle must be equal to 90 degrees inside according to rule 7. Therefore, this angle EFL is equal to 90 degrees inside according to rule 7. So in the right triangle EFL, we define this angle as alpha. So this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Therefore this first missing angle must be equal to 90 degrees minus alpha. In the next step, we extended the diameter EL by straight line until it touches the side CB of rectangle ABCD at this point. We define the touching point of the extended diameter EL with this side CB, this point as point T. By doing this construction, we created the big quadrangle ETBA. Inside the big quadrangle ETBA, we have 2 free rectangles. The sum of free rectangles is 270 degrees, so 270 degrees plus the size of this 4 pieces again. In total, must be equal to 360 degrees according to the rule that said that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this 4 pieces again must be equal to 90 degrees in its size. So inside the big quadrangle ETBA, we have 4 rectangles, and according to rule 5, any quadrangle that has 4 rectangles must be its rectangle in front of the square. So related to the big quadrangle ETBA is a rectangle because it has 4 rectangles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side BA. And again, in the big rectangle ETBA, side ET must be equal to the opposite side AB. But AB is the left of rectangle ABCD according to our definition. So we can write here that AB is the left, and from this equation ET equals to AB equals to the left, we will derive that ET is also the left of rectangle ABCD. So in total, we found out that EL is the width of rectangle ABCD and ET is the length. Okay. In the next step, we focused on the big right triangle ETG. The big right triangle ETG, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. In the next step, we prove that the big right triangle ETG is similar to the small right triangle EFL. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, this is angle E, that is a common angle that belongs to both angles. So if we found out that all the three angles of the big right triangle ETG are correspondingly equal to the three angles of the small right triangle EFL, and therefore those two right triangles are similar to each other according to angle similarity rule. So if we found out that the big right triangle ETG is similar to the small right triangle ELF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we know that the following relationship exists between their sides. we derive that side ET of the big right triangle ETG or side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. So again, for the fact that those two right triangles are similar to each other, we derive that ET over EF equals to EG over EL. So ET is the missing side, so we notice it is EF is 12, GE in total is 12 plus 10, that is 22. So GE in total equals to 22 over EL. EL is the missing side, so we leave it as it is. So here, of course, multiply this equation and find out that EF times EL equals to 22 times 12. So EF times ET times EL is equal to 21 times 22 times 12 is 264. So in total, if you found out that the area of rectangle ABCD, actually we know that we already found out that ET is the length of rectangle ABCD and EL is the width. So substitute ET by the length and EL by the width, and finally found out that the length of rectangle ABCD times the width is equal to 256 square meters. Okay. Repeat again, if you found out that the area of this rectangle ABCD is equal to 264 square meters. Okay. So we finish with the first question. In the next step, I present it to the second question, and we solve the second question of this lecture. In the second question, our mission, our task is to find out the area of this trapezoid ABCD. So it is given as the question that AB equals to AP and DP equals to DC. In addition, we know that this is line segment BQ that is equals to 4 units in its length. This is line segment QC that is equals to 9 units in its length. This is again PQC that is right angle, and those two angles are also right angles. Again, our mission is to find out the area of this trapezoid ABCD. So first of all, we defined, we know that AB equals to AP, so we define the length of AB as A. So if AB is A, then AP must be also equal to A because they are equal to each other. Likewise, we define the length of line segment PD as B, and therefore DC must be also equal to B because they are equal to each other according to what is given as the question. In the next step, we join points B and P together by straight line, and points P and C together by straight line. And by joining points B and P, we can get the right triangle ABP. So here in the right triangle ABP, the right triangle ABP is also an associated triangle because of the fact that AB equals to AP. So we have the rule that said that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides we have those two angles that must be equal to each other because they are located in front of those two equal sides. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. We know that the sum of the angles in any triangle is equal to 180 degrees, and especially to is true in the right triangle ABP. So which angles we have in the right triangle ABP? We have this angle that is the right angle plus those two angles that is alpha plus alpha is 180 degrees. So 90 degrees plus 2 alpha equals to 180 degrees. Here we subtract the 90 degrees from this equation and find out that 2 alpha equals to 90 degrees. Here we divided this equation by 2 and find out that alpha equals to 90 degrees over 2, that is 45 degrees. So those two angles are both 45 degrees, and those two angles are both 45 degrees because of the fact that triangle PDC is a right triangle and associated triangle simultaneously. Okay, so in the next step, we focus on the right side of the straight line AD at point P. So here the sum of the angles must be equal to 180 degrees according to our page. So which angles we have at the right side of the center line and this point P? We have this angle that is 45 degrees plus this angle that is also 45 degrees plus this missing angle in total must be equal to 180 degrees according to all three. Therefore, this first missing angle must be equal to 90 degrees inside. Why? Because 90 degrees plus 45 degrees plus 45 degrees, it is equal to 180 degrees. It is the sum of the angles on the right side of the center line AD at point P. So this missing angle must be equal to 90 degrees inside. In the next step, we define this angle as alpha. If this angle is alpha, then this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is the sum of the angles in a triangle. So this missing angle must be equal to 90 degrees in its size. In the next step, we define this angle as alpha. So this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. That is the size of the big angle PPC. So in the big rectangle PQC, this angle equals to 90 degrees, this angle equals to 90 degrees minus alpha. Therefore, this first missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small rectangle PQB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we prove that the small rectangle PBQ is similar to the big rectangle PQC according to angles similar to. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. This angle equals to 90 degrees according to all three. So those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that the triangles of the right big triangle PQC correspondingly equal to all the triangles of this small triangle PBQ, and therefore those two triangles are similar to each other according to angles similar to. And again, if we prove that the big right triangle PQC is similar to the small right triangle PBQ according to angles similar to. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between the sides. We derive the side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right triangle PQB. So again, I have found that PQ over BQ equals to QC over PQ. PQ is the missing side, so we leave it as it is. BQ is 4, QC is 9, and PQ is the missing side. So in total, we have found out that PQ over 4 equals to 9 over PQ. Here we cross multiply this equation and find out that 4 times 9, that is 36, is equal to PQ times PQ, that is PQ squared. So PQ squared equals to 36. We took out of this equation and found out that PQ equals to the square root of 36, that is 6. Okay. In the next step, we implemented the Pythagoras theorem on this big right triangle PBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of the big right triangle PBC is BC, so the square of the hypotenuse is BC squared, and it must be equal to CP squared plus BC squared. Okay. So BC in total is 4 plus 9, that is 13. BC squared is 13 squared, that is 169, and is equals to BP squared plus PC squared. Okay, again, it's a formula that BC squared equals to BP squared plus PC squared. BC is 13, therefore BC squared is 13 squared, that is 169, and it is equals to BP squared. What is the value of BP squared? In the right triangle APB, A squared plus A squared equals to BP squared. So BP squared is equals to A squared plus A squared, that is 2A squared. Okay, again, BP squared is 2A squared plus PC squared. What is the value of PC squared? If we focus on the right triangle PDC, PC squared must be equal to B squared plus B squared, that is 2B squared. So PC squared equals to 2B squared. So in total, we found out that 169 equals to 2A squared plus 2B squared. So 169 equals to, if you took out a 2 as a common factor, so inside the brackets we left only if A squared plus B squared. We divided this equation by 2 and I found out that A squared plus B squared equals to 169 over 2. Okay. Our mission, our task is to find out the area of this trapezoid ABCD. The area of trapezoid ABCD must be equal to the sum of the areas of the three components that it consists of. Again, the area of trapezoid ABCD must be equal to the sum of the areas of the three components that it consists of. The big trapezoid ABCD consists of the right triangle ABP, it is also consists of the big right triangle PBC, and finally it consists of the right triangle PDC. So the sum of the areas of those three components that trapezoid ABCD consists of must be equal to the area of trapezoid ABCD. Okay. Repeat again, I shall find out that the area of trapezoid ABCD must be equal to the sum of the areas of the three components that it consists of. So first of all, found out the area of the first component, that is actually the area of the small right triangle PBC. It must be equal to the base, that is BA, times the height, that is AP over 2. So it is A times A, that is A squared over 2. So if you found out that the area of the first component, that is the right small triangle ABP, is A squared over 2, plus the area of this big right triangle BPC. What is the area of the big right triangle BPC? This equals to the base of the triangle, that is BC, times the height, that is QP over 2. So if again, I shall find out that the area of the big right triangle PBC is equals to the base BC times the height QP over 2. And we have also the area of the third component, that is the area of the big right triangle BDC. The area of the big right triangle BDC must be equal to the base DC times the height, that is DP over 2. So this B square, again, the area of the right triangle BDC is equals to B square over 2. Because again, the area of the right triangle PDC is B square over 2. So A square over 2 plus B square over 2 is A square plus B square over 2. PC is 13, PQ is 6 divided by 2. 13 times 6 over 2 is 6 over 2, that is 3 times 13. 3 times 13 is 39. So in total, we have found out that the area of trapezoid ABCD equals to A square plus B square over 2. But we have already found out that A square plus B square equals to 169 over 2. So we substitute A square plus B square here by 169 over 2. So A square plus B square is 169 over 2, and we have to divide it by 2 again. So it is times 2 again, plus 39. 2 times 2 is 4, so in total this expression equals to 169 plus 169 over 4 plus 39. Here we multiplied 39 by 4, and then we divided by 4 in order to have a common factor with this number. I finally found out that the area of trapezoid ABCD equals to, in the numerator we have 169, and We have also 39 times 4, that is 156 divided by 4. 169 plus 156 is 325 divided by 4. 325 over 4 is 81.25 square units. So in total, we found out that the area of this trapezoid ABCD is equal to either 325 over 4 square units, so in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. Okay, thank you very much.